Hello everyone, I'm Qian. Today I'm going to present our work Fast Forward Reality, altering error-free context over policies with real-time unit tests in extended reality. This work was completed when the Internet Meta Reality Labs. I'd like to express my gratitude to the co-authors Tianyi, Xuhai, Tanya, and my internship mentor Cash for their invaluable support during my internship. Alright, let's get started. As intelligent environments and ubiquitous computing progress, context-aware policies, or CAPs, are being integrated in our everyday lives. Typically, a context-aware policy is an application predefined by an end user that automatically triggers digital functions when one or more contexts happen. For instance, in commercial CAP ordering tools like If This Then That and Alexa Routine, one can order simple CAPs such as turn off all lights when I leave home or play pop music at 7 p.m. Recently, the development of augmented reality, deep learning, and the Internet of Things has made it possible to detect an increasingly wider range of contexts in real time, including human activities, proximities, and the states of smart objects. This, combined with general contexts such as time and calendar events, has led to promising advancements in the research field of context-aware policy authoring. As mentioned before, context-aware policies are highly personalized. They become beneficial in our lives only when we have established preferences or routines in our day-to-day activities. However, as end users have more and more choices of available context during authoring, how to ensure the authored CAP still perfectly behaves as expected back in our everyday life? In specific, two typical errors may happen in such CAP authoring and running. Imagine Bob is watching TV while having dinner. He creates a CAP to trigger such a relaxed moment in the future, turn on the living room TV when I'm eating. However, another day in his study room, when he was struggling with a paper deadline while biting a sandwich, the TV in the living room is on. In this example, during authoring, the context included in the policy were under-specified, which may result in some annoying moments like this one during the runtime. Alice, on the other hand, simply grabs all present contexts in her living environment to author a CAP, play my yoga music list when I'm doing yoga in the living room in the morning. In another evening in her bedroom, she starts yoga practice, but no music is played. Here the CAP is overspecified. It doesn't cover all desired scenarios to trigger the action. Given this concern, is there any way that end users can get rid of these runtime errors beforehand? Unit tests seems to be a suitable solution. By comparing the function outputs with ground truths after providing carefully designed unit test cases, professional software engineers could verify whether the function performs as expected. Researchers have proposed multiple unit test generation architectures to validate the context-aware applications using simulated context data. For instance, some works target general contexts such as cell phone locations for delivery apps or temperature and smoke sensor data for fire detection apps. We acknowledge the effectiveness of this process and want to adopt it in our scope, but two issues still remain. First, when it comes to user-customized CAPs for everyone assistance, and when such process is run by an end user who even don't know coding, how to generate test cases that are specific for the user and the environment. Meanwhile, when users don't have the corresponding expertise, how to let the user be able to identify whether the CAP performs as expected, or say identify what's wrong in that CAP, so that the user can refine it accordingly. Extended reality, or XR, holds the potential to resolve these two concerns. First, researchers have envisioned scenarios where users wear XR headset in everyday life, while the device is able to pervasively record users' surrounding context, including activities, interactions with smart objects, locations, as well as general context such as time, and even abstract context such as calories intake. This personalized context history contains rich details about the user's personal preferences and daily habits, making it an excellent source for creating user-tailored test cases. On the other hand, the in situ visualization of XR assets facilitates users to interpret the semantic relationships with respect to the attached objects. With proper visualization, it can even create illusion of non-present realities, which also matches the needs of showing imaginary context in the test cases of CAPs. Inspired by these prior works, we present Fast Forward Reality, a novel workflow that enables users to author, test, and refine CAPs via real-time unit tests in XR. Before I dive into the system design, let me clarify the framework of CAP authoring adopted in our paper. Here are the context factors we consider in our system design. We follow the fact that most off-the-shelf real-time context detection techniques output discrete labels. Please refer to the paper for the corresponding techniques and research projects. For each context vector, we define context instances, which are considered to be the discrete labels of the context detection outputs. Thanks to the capability of XR, as we mentioned before, we envision the context history of an end user and the surroundings can be pervasively recorded and stored as a multi-dimensional time series. In specific, whenever a perceived context instance changes, the recorder can add a new line of data, context scene, to the context history, which holds all the present context instances. I'd like to point out we propose a way of storing personalized history of the user and the surrounding, but the implementation of the context detection techniques is out of our paper scope. Then we adopt the trigger action metaphor to alter a cap. Let me use an example to explain. The trigger contains 3 location context instances, an eating activity context instance, and a music player off object state context instance. The action is TV on object state. During the runtime, we propose to follow a certain logic check progress to determine whether the cap should be triggered. For instance, at any present context scene, if the user is eating at one of the 3 locations while music player is off, the cap will be triggered to turn on the TV. Now let me talk about system workflow of our system. In general, our system adopts this order test refine workflow to help the user order and iterate the cap with unit testing until all test cases meet the user's expectation. First, let's take a look at the test case generation algorithm. So what is a test case in our framework? It is a set of context instances, but unlike the trigger, a test case can only have at most 1 context instance for any context vector available in the environment. It represents an imaginary moment when the involving context instances happen. As we mentioned at the beginning, cap validation is highly personalized. In order to effectively validate a cap, we identify 3 main strategies to generate high-quality test cases. A test case should have high possibility to happen in the user's real life. A test case should help user identify potential mistakes of the current cap. And the test case should be as simple as possible to reduce users' mental load. To address these 3 goals, we propose to calculate 2 values from the user's context history to support test case generation. First, the uncertainty coefficient. I won't cover the details of the calculation, but this coefficient is based on conditional distributions and represents the correlation between 2 context vectors. For instance, if the uncertainty coefficient of activity and time context vectors are higher than the threshold, which means the user oftentimes does some specific activities at specific times. For concurrency count, it represents how frequent a specific context instance happens with respect to the context vector. For instance, in the context history, there are 50 context scenes, or say rows of data. For the activity context vector, eating happens 15 times, using phone happens 17 times, and so on. Referring to these 2 values, we design the test case generation algorithm. Each run of this graph will iterate all available context vectors in the context history, which generates a series of test cases for 1 context vector included in the original cap. Here, assume the initial cap is turn on the TV when I'm at a living room sofa. And there's only 1 context vector included in the cap location. Let's say at 1 iteration, the target context vector is activity. After this run, the generated test case is eating at living room sofa. What does it mean? It means according to this user's context history, the location has a high correlation with the activity. But seems like the user doesn't include any activity. So the algorithm is trying to tell the user, please consider this situation by adding a frequently happened activity eating to the test case. Due to time limitation, I won't cover too many details. Please refer to our paper for more examples and implementations details. Now let me introduce the XR ordering interface, which is in situ rendered either in user's physical environment or in its virtual replica. We envision the smart objects such as music player, coffee maker, and TV can not only provide their states but also their locations within the environment. Registering smart objects in XR spaces has been explored by prior research and is out of our paper scope. Here, the user is ordering the turn on the TV when I'm at living room sofa cap, which is mentioned. Available smart functions and location context instances are in situ placed in the environment. Users can simply check them to add them to the cab, and the cab is shown on the hand menu. After the user enters the test mode, the system lists all test cases in the user's hand menu, and the user can browse them one by one. When the test case is activated and involved context instances are highlighted in the XR environment. To better help the user understand this semantics, we support users to act out some context factors such as location and object state. We also provide XR overlay visualization of other context factors such as time and activity. Here the system generates the eating a living room sofa test case, as we just mentioned before, and the user acts out the test case. According to what is currently ordered, the TV is on. Although this test case triggered the ordered action, it still reminds the user to consider adding some activities in this cab to make it more constrained. So the user goes back to the order mode to refine the cab. By repeating the test and refine, the user iteratively creates a cab that accurately reflects the user's intention and the diverse scenarios. To evaluate the usability of our system, we conducted a 12-participant user study. It was held in a virtual apartment environment. Each user completed 2 cab ordering tasks, a smart TV controller, and a smart music player using fast-forward reality and baseline system. The order was counterbalanced. Since one of the key contributions of this paper is the unit test idea, we set a baseline system to have the same XR ordering interface, and the test mode was still available, but no generated test cases. If wanted, the user could test the cab with manually selected context instances. The user will ask to order the cab using both systems until they feel confidence about cabs. Since the test case generation algorithm relies on highly personalized context history, before they came, we sent out a pre-study survey collecting their preferred context instances related to the smart music player and TV controller. After they came, we provided a 2D tool for the users to create fake context history, where the context instances were set according to their survey responses. Another purpose of this tool was to use the context history as a ground truth to quantitatively evaluate ordered cabs. Let me highlight some user study results. First, the test case generation algorithm was proved to be effectively improved the cab accuracy. We also received positive feedback that generated test cases were reasonable and highly relevant to the cab and their personal preferences. Like here, fast-forward reality could give me some counterexamples that I even didn't realize it would also trigger the action. Regarding the adoption of XR as the order and test interface, we also received the positive feedback. If the cab will be consumed in my room, it makes so much sense to create and test it right here. I felt much more confident about my cab when I saw the TV was on after I sat on the sofa. I'd also like to highlight 2 discussion directions reviewed from the user feedback. First, we've emphasized that cabs are tailored to each user's personal preferences, but how to balance between personalization and the scalability in cab validation could be a potential research direction. For instance, during testing, can the system let users define alternate contexts when some contexts are changed or not available in different environments? Another critical point to raise is that our system cannot deal with the errors caused by those context detection modules and the uncertainty of us human beings. For AI errors, even a validated cab can be wrongly triggered if an activity detection module returns a wrong label. Similarly, humans will never mechanically repeat the routines exactly same every time. There's always some time the user wants to do something different, but the cab doesn't know. What can we do to mitigate these errors and to let users still trust our system deserves further exploration as well. Last but not least, I want to expose some future works based on our system limitation. First, users may order more than one cab to run at the same time. We propose to improve the test case generation algorithm to take into consideration the potential conflicts with existing cabs. Meanwhile, we could provide assistance to reduce the workload of using our system, such as provide template cab based on users' context history and suggest refine the cab after some initial edits. Finally, the privacy concern. The system should consider the scenarios when users don't want to share some of the context and adjust the test case generation algorithm accordingly to reflect the user's privacy concerns. That's all. Thank you.